the P block, we now discuss oxides. The point or the phenomenon that is specific to oxides is which is para, which is dia. Which is para and which is dia. Even with other molecules, this magnetic nature is relevant, but it is more relevant with oxides. So, let me give you a simple procedure. One capital, where you have only one capital letter in the symbol, one capital, no unpaired electron, UPE, unpaired electron. No unpaired electron, the species is said to be diamagnetic. The species is said to be diamagnetic, whether it is a molecule, whether it is an atom, or whether it is an ion. No unpaired electron, dia. And if unpaired electrons are present, yes unpaired electron, it is para. Of course, copper is a chief exception. Copper is an exception to this. What do I mean by one capital? Let me specify. Suppose you have Na, sodium. In its electronic configuration, you have 3s1. You have that unpaired electron 1. Therefore, it is para. Sodium is paramagnetic. And aluminum 2 plus. Aluminum 2 plus. Aluminum, you know the electronic configuration 3s2, 3p1. After removing 2 electrons, it is again 3s1. You have an unpaired electron, para. But what about aluminum plus? Aluminum plus is 3s2. So, all these species have one capital letter. Where you have one capital letter, you just look at their electronic configuration. And this is for more than one capital. More than one capital, or the species should contain a number like O2, N2, etc. More than one capital. The rule, this is for one capital letter and this is for more than one capital letter or number. Total number of electrons, is odd number, then it is paramagnetic. And total number of electrons, if it is even, then the species is said to be diamagnetic. Right. Let us apply this for NO. That is why I said this magnetic nature is relevant in oxides, more relevant in oxides. NO, nitrogen has 7 plus 8, 15, which is odd, therefore it is paramagnetic. But you have O2, B2, N2, 2 minus and S2 are exceptions. What do you mean by that? They have even number of electrons but para. O2, if you look at O2, 8 plus 8, 16, even but para. They are all even but para. Like, similarly, look at copper. It is 3d10, 4s1. You have an unpaired electron, but still it is copper is diamagnetic. Even though it has an unpaired electron, it is diamagnetic. So, NO, let us look for more examples. NO2, 7 plus 16, the atomic number of nitrogen of course is 7, O2, 7 plus 16, 23, odd, therefore it is paramagnetic. So, it all depends on the total number of electrons where you have more than one capital or number in it. O2, 8 plus 8, 16, even, but I told you it is an exception, even but paramagnetic. Whatever be the reason, let us not look at the reason now, because it is enough if you know whether it is diamagnetic or paramagnetic. H2 plus, what rule you will apply? It is, you have a number here, H2. So, total number of electrons is just 1, therefore odd, therefore para. So, NO2, ClO2, they are all paramagnetic, and H2 plus is odd number and then it is paramagnetic. So, oxides of P block, where we have looked at the magnetic nature, apart from shape, hybridization, oxidation state, etc., you need even to know whether it is dia or para, magnetic nature. Next point, nature of oxides, whether they are acidic or basic or neutral. Very few in our syllabus are neutral oxides. Neutral oxides. I strictly confine to the JEE syllabus. We have 4 neutral oxides in our syllabus: CO, NO, N2O, H2O. These 4 are neutral oxides, neutral to litmus. They are neither acidic nor basic. Neutral means neither acidic nor basic. And the second set, amphoteric oxides. Amphoteric oxides. Once again, I repeat, we confine to our syllabus only. Outside our syllabus, there is, I think, chromium oxide, CRO, chromium monoxide, which is between neutral and amphoteric. There is no, once again, there is no clear-cut yardstick to separate this is acidic, this is basic. And amphoteric oxides, all the oxides of beryllium, aluminium, zinc, gallium, stannum, plumbum, tin and lead, arsenic, antimony, and TeO2, tellurium dioxide. What do I mean when I said all the oxides? I mean all the oxides of all these elements. Stannum forms a monoxide and a dioxide, SNO, SNO2, PbO, PbO2. Arsenic forms trioxides and pentoxides, you know, As2O3, As2O5, and once again Sb2O3, Sb2O5. So, all the oxides of all these elements, there may be 1 or 2 outside this list, but it is enough if you know the large majority and whichever are asked very frequently. Cr2O3 may be considered as amphoteric, but I don't dare put that in here, because let's not discuss ambiguous things. And now, once you verify these 2 lists, you percolate through this list, and then 3 amphoteric oxides. All other metal oxides, are basic. All other non-metal as well as half metal oxides are acidic. Like even the tellurium trioxide, TeO3, is also acidic. SeO2, SeO3, they are also acidic. So, all other non-metal half metal oxides are acidic. Right. So, I will just give you an example and you may have to say 1, 2, 3, 4. When you say 1, you are telling me it is a neutral oxide. When you say 2, you are telling me it is an amphoteric oxide. And 3, it is a metal and it is metal oxide and basic. So, not only you are telling me it is a basic oxide, and you are giving me the reason also. Like NO2, where did you get it? NO2. It's like it's not here, it's not here. Non-metal oxide, therefore 4. When you said 4, when you say 4, what are you telling me? It's an acidic oxide, NO2 is an acidic oxide because it's a non-metal oxide. Even the oxides of germanium, which is a half metal, even the oxides of germanium are also acidic oxides of germanium, and even selenium, which is a half metal, and tellurium trioxide, TeO3, these are all. Next, CO2. What do you know about carbon? Carbon is a non-metal. and carbon dioxide is a non-metal oxide. Therefore, once again it is acidic. 4. SO2, non-metal oxide. 4. Al2O3, aluminum oxide. Of course, aluminum is a metal, but aluminum is in the amphoteric list. Aluminum oxide is amphoteric. Gallium oxide, zinc oxide, beryllium oxide. You don't know the significance of what we have done now. Like, if a substance is amphoteric, if an oxide is amphoteric, even the metal is considered to be amphoteric. It can react with both acids and bases. Generally, metals react with acids. Metals generally react with acids. A metal reacting with both acids and bases is said to be amphoteric. And a metal hydroxide, zinc hydroxide. Generally, metal hydroxide, we expect them to be bases. But zinc hydroxide is soluble in another hydroxide, NaOH. Zinc hydroxide dissolves in sodium hydroxide. How come? Zinc hydroxide is basic, but that's a base reacting with another base, that is called amphoteric. It has both acidic and basic nature. This principle is very interesting. We have in a different topic, we definitely look at this, but once you learn a particular phenomenon, if you know the application also, the learning will be permanent. So I am just giving this example. How will you separate a mixture of Al2O3 and Fe2O3, which is a part of roasted bauxite that is heated strongly in oxygen? Roasted bauxite. This is red bauxite. Roasted red bauxite. It contains Al2O3, Fe2O3. You have to separate them. It's a mixture. Okay. This is amphoteric. Amphoteric means acidic and basic. But this is acidic and basic. Both acidic and basic. Fe2O3 is strictly basic, is only basic. Therefore, so to separate them, if you add an acid, both of them react with acids. HCl. Al2O3 reacts with HCl, Fe2O3 reacts with HCl. Therefore, you use a base called NaOH, which precisely reacts with this only. NaOH reacts with Al2O3 only, exclusively. It doesn't react with Fe2O3 because this is basic. But what about Al2O3? Both acidic and basic. Therefore, this is selective reaction. NaOH reacts with Al2O3, between Al2O3 and Fe2O3 selectively. This selective reaction is called a leaching. What does a leech do? Leech is a marine animal which sucks blood only. It doesn't touch human flesh. It just simply sucks your blood. Leech. Therefore, the process is called leaching. Selective reaction. When there are two substances here, the third substance preferably reacts with the first one only, with one of them only, and that is called leaching. So, this reaction depends on what? This reaction depends on the amphoteric nature of Al2O3. If both were basic, I could never have used a base. If both were acids, I could never have used an acid to separate them. Therefore, since this is both acidic and basic, we have applied this amphoteric nature elsewhere in metallurgy. So, what are the two areas specific to oxides only? Magnetic. So, what is it you have learnt? NO2. Under this heading, we know the structure, oxidation state even before the heading oxides. You know that NO2, N double bond O, dative bond O, and there is a single unpaired electron. You know the structure. You know the oxidation state is +4. You know that it has a bent shape. You know the hybridization is 5 plus 0 by 2, 2.5. 5 plus 0 by 2, 2.5. The next integer 3, you call it sp2. The hybridization is sp2. The hybridization, the shape, the oxidation state. These are there for all species, all molecules, whether it is an oxide or a halide or an oxyacid. You should know the structure, oxidation state, shape, etc. But the question that is specific to oxides is NO2. What is it we have learnt under this heading specific about NO2? What is that we have learned specific about NO2? It's paramagnetic and it's an acidic oxide. So, you know this magnetic nature and acidic nature are mostly relevant in oxides. Not that other substances don't have this acidity, but this is more relevant to this one, oxides. Now, this is a broad picture of the periodic table. Elements towards the left, they are more electropositive. More electropositive. What does it mean? Elements towards the left side of the periodic table are more electropositive, more metallic, and better reducing agents. Better reducing agents, and oxides are more basic. Look here. Elements towards the left side of the periodic table, and they are the opposite. They are more electronegative. I am just writing the opposite, more electronegative. Electropositive, electronegative, more non-metallic. Better oxidizing agents. And oxides are more basic. Here you are, plus, minus, minus, plus. So, what is that now you understand? From left to right in the periodic table, the acidity of oxides increase. Oxides are more acidic. Basic, the opposite is acidic. And plus, minus, minus, plus. You just remember this shorter version, plus, minus, minus, plus. Top to bottom, left to right. Now, between sulfur and chlorine, which is a metal? Between sulfur and chlorine, which is a metal? No one is a metal for that matter. Neither sulfur is a metal nor chlorine is a metal. But what can you say about sulfur? Sulfur being left side in the periodic table, you can say sulfur is more metallic, but you can't say that sulfur is a metal. Sulfur definitely is not a metal, but sulfur is more metallic than chlorine. So, none is the answer between sulfur and chlorine, which is a metal, none. But what can you speak for sulfur? It's more metallic. Among magnesium, aluminum, silicon, sodium, 4 elements belonging to the third period, all of them belong to the third period. Which is most electropositive? You generally tend to say towards the left. Okay, it's okay, magnesium is on the left in the list I have written, but you have to arrange them according to the periodic order, not the order in which the question is given. Look here. You just arrange them. Sodium, magnesium, aluminum, silicon. You arrange them according to their atomic numbers, 11, 12, 13, 14. And now, towards the left, what is that you know? Towards the left, elements are more electropositive. Sodium is more electropositive. Sodium is more electropositive. Silicon is more electronegative. Left, right, you have to say only when you arrange them according to periodic order, 11, 12, 13, 14. 11, 12. So, elements towards the left, more electropositive, more electronegative. So, sodium is a better reducing agent, and oxide of sodium, sodium oxide, is most basic. Now, let me write the 7 oxides, Na2O, MgO, magnesium oxide, Al2O3, SiO2, P4O10, SO3, Cl2O7. All of them belong to the same period, 11, 12, 13, 14, 15, 16, 17 or their atomic numbers from left to right. And there is one more thing that is common. Here +1, oxidation state of sodium is +1, +2, +3, +4, +5, +6, +7. I have taken the oxides of third period in their highest oxidation state. Oxides of third period in their highest oxidation state, and Na2O. What can you say about Na2O? Highly basic. Highly basic. What can you say about magnesium oxide? Basic. Basic. Al2O3. It is amphoteric. Amphoteric. And SiO2, weakly acidic. It's a very weak acid. Silicon dioxide, when dissolved in water, you get a very weak acid. Weakly acidic, acidic, highly acidic. And that one is very highly acidic. Very highly acidic. So, left to right, what is it you observe? Highly basic and highly acidic. Yes, you know, acidity of oxides increase. So, you can compare oxides in their highest oxidation state. Don't ask me to compare P4O6 and maybe SO2. P4O10 and SO2. So, phosphorus in its highest oxidation state, sulfur in its second highest oxidation state, that perhaps I may not be able to compare. There is no rule for that. But here, +5, +6, SO3 is more acidic. More acidic than P4O10. Left to right. You know what happens top to bottom also. Top to bottom. This is plus, minus, minus, plus. So, what is expected to happen? The opposite. Basic, acidic. Acidic, basic. All negative properties, all positive properties you attribute. Now, among NH3, PH3, ASH3, SBH3. So, among NH3, PH3, ASH3, SBH3, BIH3, who do you think is most basic? You may want to apply minus plus. Minus means more acidic, more basic. Is it correct? Do you think it's correct? No. Why? The rule was given for oxides, mind you. Oxides are more acidic. If it had been N2O5, Bi2O5, yes, the rule could be correct for oxides, but these are hydrides. So, don't get carried away. The rule I have given is for oxides, don't apply that for hydrates. What's the rule for hydrates? Okay, we'll discuss later. Now, that's all about oxides of non-metals. Perhaps you knew everything that you need to know about oxides of non-metals. Of course, some structures like P4O10, P4O6, they have a special structure. We will discuss that under a separate heading. And now, halides. As I have been repeatedly telling you, there are so many general things that have to be learnt about large majority. For example, you have PCl3, a halide. What should you know about PCl3? As a student of JEE, PCl3, you should know that phosphorus is in +3 oxidation state, because you know chlorine is more electronegative than phosphorus. Chlorine being more electronegative, the oxidation state of phosphorus is +3. Now, PCl3 the structure, and 3 bond pairs, 1 lone pair. So every time, don't tell me, sir, you have told this 100 times. Yes, I told this 100 times only to tell you this oxidation state, these lone pairs, and the shape pyramidal. So the shape, the hybridization, the oxidation state. What is hybridization? 5 plus 3 by 2, sp3. So the shape, the hybridization, the oxidation state, the structure, they are relevant with oxides, halides, oxyacids, hydrates, what not, all compounds. They are relevant for all molecules. So we need not study them again. This is the last time I will be mentioning this, the last time. So you make sure that you know the oxidation states, shape, lone pairs, hybridization, whether polar or not, lone pair is present, therefore polar, whether polar or not. And I believe I have given the rule, polar, if the lone pair is present then it is polar, and no lone pair but similar terminal atoms like PCl5, all 5 are chlorines, PCl5. So no lone pair and similar terminal atoms, that is said to be non-polar. But lone pair is not present but dissimilar terminal atoms like CHCl3. No lone pair but dissimilar terminal atoms. So what is this? This is again polar. Dissimilar itself means polar. So case 1, if lone pair is present, polar. If lone pair is present, polar. Let me give the rule for polarity. 1. If lone pair is present, polar, except XeF2, XeF4, XeF2, XeF4, ICl2 because though there are 3 lone pairs in ICl2, it's again a linear molecule. ICl2 and linear, symmetric. If lone pair is present, then it's polar. You can even write ICl2, interhalogen compounds. 2. No lone pair, but dissimilar terminal atoms. Once again polar. Polar. Case 3. No lone pair and similar terminal atoms. Non-polar. Let me give an example and you have to tell me whether it is 1 or 2 or 3. NH3, it's a hydride. Why am I teaching hydrates under the heading halides? It's not important for me whether it is a halide or a hydrate. There are some halides which are polar, there are some hydrates which are polar. So we should study polarity. Polarity of halides, polarity of hydrates, polarity of oxides, everything. So NH3, lone pair is present, case 1. So if you say 1, what are you telling me? 1, lone pair is present, therefore it is polar. SOCl2, lone pair is present, polar again. SO2Cl2, no lone pair, but still you have dissimilar terminal atoms. 2 are oxygens and 2 are chlorines. Sulfur is attached to 2 oxygens and 2 chlorines, therefore non-polar, dissimilar. 2. Boron trifluoride, yes, boron trifluoride. There is no lone pair, there is no lone pair, and the terminal atoms, all 3 are fluorines. 3. Like that. CH4, of course, no lone pair, similar terminal atoms, and 3, non-polar. So just by observing whether there is a lone pair or not, and by observing whether there are similar terminal atoms or not, you can say whether a molecule is polar or not. PCl3 is polar, PCl5 is non-polar, SnCl2 is polar, SnCl4 is non-polar. So, there lies a lot of difference. SnCl2 dissolves in water, but SnCl4, of course, SnCl4 also dissolves in water because of different reason, but SnCl4 dissolves in non-polar solvents also. SnCl4, because it is non-polar, it can dissolve in non-polar also. SnCl4 dissolves in water because of its a particular special reaction with water. So, there is only one question that is specific to halides, because the others are common to all sets of compounds, all types of compounds, but halides there is only one point. Like in oxides, there you needed to know whether it is diamagnetic or not or paramagnetic or not. In halides there is only one point, that is their reaction with water. Halides reaction with water. How does PCl3 react with water? So, let us now discuss the reactions of all substances with water, mostly halides. Now, hydrolysis, hydro plus lysis, hydrolysis, hydrolysis. Hydro means water, lysis means breaking. The term comes from analysis, analyze, breaking. So, hydrolysis means breaking a molecule, with the help of water. Breaking a molecule with the help of water. You can compare this with other lyses. Electrolysis, breaking a molecule with the help of electricity, electrolysis. Pyrolysis, pyre means fire, breaking a molecule with the help of electricity, which is thermal dissociation, electrical dissociation, breaking a molecule with the help of electricity. Breaking a molecule with the help of electricity, breaking a molecule with the help of heat, thermal dissociation. Ozonolysis, what is ozonolysis? Breaking a molecule with the help of ozone, ozonolysis. Alcoholysis, breaking a molecule with the help of alcohol. Ammonolysis, breaking a molecule with the help of ammonia. Solvolysis, breaking a molecule with the help of a solvent. So, all these are synonymous terms. Now, breaking a molecule with the help of electricity. We have a simple off the track procedure. This is not a rule, let us not call it a rule, but this is a procedure to remember at least 100 reactions. 100 reactions, there is a simple single step procedure. 1. XY, suppose you are asked to break a molecule called XY. XY, how does XY react with water? Break the bond, H on one side, OH on the other. Just put H on one side, OH on the other. You know, this H is not H, this is H plus, OH minus. And where will H plus go? There is no big deal in it. You know, H plus goes to whoever is more electronegative. Whoever is more electronegative. How do you know which is more electronegative? F greater than, O greater than, N greater than, Cl greater than, hydrogen greater than, boron greater than, F, O, N, Cl, H, B. OH minus, more electropositive. Whichever is more electropositive, more electronegative. Which is more electropositive? Generally metals. which have calcium, magnesium, which have U in them, UM in them, more electropositive. So, second step. Third step, use any number of H plus or OH minus. Use any number of H plus or OH minus as the valency demands. Suppose if you are breaking 3 bonds, you give freely 3H and 3OH. PCl3, you will be breaking 3 bonds between phosphorus and chlorine. So, feel free to use any number of H plus and OH minus. Now, fourth point in hydrolysis, maximum number of OH groups. Though we give more OH to a particular atom, it does not retain all the OH groups. There is a maximum. For example, silicon 4, phosphorus and boron can retain 3. Sulfur just 2 OH groups, and chlorine, bromine, iodine, nitrogen, carbon, all of them can take only 1, and beryllium and xenon, none, not a single OH group can be attached to them. What happens if you give more OH groups? Automatic loss of water takes place. HOH will go away and a double bond O will be formed between 2 OH. Only one oxygen remains, H2O will go away and that oxygen forms a double bond with the central atom. Now, symbols for hydrolysis. Symbols for hydrolysis like H2O, H plus. When you see this H2O and H plus, you should know the reaction demands you to hydrolyze. H3O plus or simply water, H3O plus. Dilute H2SO4, dilute acid. In more cases, the presence of dilute acid should remind you of this hydrolysis reaction. And even H2O, OH minus, aqueous KOH, all these should first remind you hydrolysis. Or if this particular species doesn't have any, means aqueous KOH, if you know the particular reaction, you proceed. If you don't know what the reaction, then suspect hydrolysis. For example, if you use aqueous KOH with carbonyl compounds aqueous KOH, it's aldol reaction. So, if there is no other specific reactivity for aqueous KOH, dilute H2SO4 when added to alkenes, hydration will take place. I am not asking you to hydrolyze there. Of course, in fact, there that is also hydrolysis, breaking the bond HOH. But if it has a specific reactivity, you proceed. But if it doesn't have a reactivity and you are in doubt, then you suspect it may be hydrolysis and the situation may demand hydrolysis. The last point, 6. No hydrolysis for whatever be the reason, these following compounds do not undergo hydrolysis. That's not going to the details why they don't undergo hydrolysis. It's enough if you are able to deliver the goods. No hydrolysis for carbon-carbon bond, carbon-hydrogen bond. Why? There is no polarity. Where do you break the bond? H on one side, OH on the other. Where will you write? And CC, carbon-carbon bond, carbon-hydrogen bond, and of course CCl4, it doesn't undergo hydrolysis. Any strong bond, this is a vague term. How do you know which is very strong? Generally, if you think it's a very strong bond, you can't hydrolyze that. So, any bond involving fluorine, except with boron and xenon. The boron-fluorine bond can be hydrolyzed and the xenon-fluorine bond also reacts with water. So, because fluorine forms very strong bonds, you can't break the bond. You can't say break the bond. It is easier said than done, mind you. Now, of course, in a different context, we, This hydrolysis I am telling you is not a textbook procedure. Of course, it is there in some standard books like General Chemistry by Cinco and Plain. The procedure has been mentioned, but it's not any, I mean, what you call a standard, but it's like more or less like a shortcut, or so much to say, you can remember at least 100 reactions using this procedure instead of mugging them up. And salts of strong acids and strong bases, they don't undergo hydrolysis, I am telling you, in a different context. Reaction with water producing acid and base molecules, but since no hydrolysis, the heading stands good for all these things. Now, and here is a warning, you learn the hydrolysis of xenon fluorides from a textbook, they don't follow, okay. Hydrolysis of xenon fluorides you study from NCERT, okay. Note, don't tell me later, sir, this procedure is not exactly the same for xenon fluorides. So, note, hydrolysis of xenon fluorides. Study from NCERT. Just 3 or 4 reactions are given. They don't exactly follow the procedure. I will tell you. Hydrolysis of xenon fluorides. Halides. Let us hydrolyze some of the compounds. Calcium carbide. Calcium carbide. How will you hydrolyze that? Break the bond. 2OH, 2H. 2OH and 2H. You get CaOH twice, C2H2. Acetylene. Why have I given 2OH? The valency of calcium demands 2 OH groups. Calcium belongs to the second group. And why have I given 2 hydrogens only, whereas carbon can handle 4 hydrogens? You should know the structure of calcium carbide. This is calcium carbide. Break the bond. HOH. OH minus is given to the metal, calcium. Calcium metal, OH minus is given to calcium. HOH again, calcium hydroxide. So, definitely you will now ask me, sir, should we know the structure before we hydrolyze? Yes, but only in 2 cases, only with 2 molecules, you better know the structure first before you hydrolyze calcium carbide. In all other cases, you can blindly adopt this procedure. You simply break the bond, HOH. Calcium carbide and hydrolysis gives acetylene. And I forgot to give among that list deuterolysis. Break the bond with heavy water. Deuterolysis, breaking a molecule with the help of heavy water. So once again, calcium carbide on deuterolysis gives what? Break the bond, instead of HOH, you put DOD. You know, H2O is water, D2O is heavy water. HOH, DOD. Wherever you have hydrogen, you just replace the hydrogen with deuterium. Now, aluminium carbide, Al4C3. How will you hydrolyze? Break the bond. 4 aluminiums, 4 3s are 12 OH, 12H. Why 12 this time? Yes, aluminum is Al3 plus, carbon is C4 minus, carbide C4 minus. So, what you end up getting is 4 AlOH thrice. 4 AlOH thrice plus 3 CH4. 3 molecules of methane. 4 AlOH thrice, 3 CH4. 4 aluminum hydroxide and 3 methane. Al4C3. Now, aluminum carbide on hydrolysis give methane. So does beryllium carbide, Be2C. Why have I given 12 OH here? You should know 4 into third group, aluminum, its valency 3. Break the bond. 2 berylliums. 2 into 2, 4 OH. 4H. you got BeOH twice. So you may be surprised the heading is halides, but why are you discussing carbides? So you have been observing the pattern in which we are studying. If we study hydrolysis or reaction with water, we study the reaction with water of all compounds. How does any compound react with water? And of course, halides is only a part. So we study the reaction of halides also with water. But since the procedure is same for everything, we have to study all reactions wherever water is involved at one place. That is how you have to make a systematic study. Now, beryllium hydroxide, methane. But you know, beryllium doesn't handle even a single OH. If you remember the maximum OH list, remove water, automatic loss of water, you end up getting BeO, beryllium oxide, and methane.